Hello everybody, in this tutorial we're going to use Ansys Fluent to simulate steady state laminar flow around a cylinder in a channel. So this is a relatively classic case. So in the book by Furtziger and Perich, they also analyzed this case in 2D and 3D. And it's interesting because depending on the flow velocity or Reynolds number, you get a variety of different flow conditions. So you might get laminar flow, or you might get vortex shedding that's laminar, or you might even get turbulent flow. So they look at it in 2D and 3D. So I've uploaded this excerpt if you want to look at it. Okay, so we'll open up Workbench. So remember, just search down here for Ansys Workbench, open it up. First thing, as always, you're just going to save the file. So I save them in my documents. Here. So remember that when you save this workbook project file, it makes a folder as well. So actually most of the model contents are stored in this folder. So if you're backing it up, make sure to copy both of those. So I'm going to call this flow around cylinder and save. Okay, so we're going to have a Fluent analysis system. So just drag it left click and hold and drag across. And call it flow again. So if I wanted to have multiple ones, I could call this mesh 1 or mesh 2 if I wanted to do a mesh sensitivity analysis here. And click on geometry over here on the right. I'm going to set it to 2D. So now we're going to just double click on geometry. That'll open up the default geometry generation software. So that's space claim. But of course, you could always right click and import geometry, or you can use Design Modeler, which is a different CAD software that's built in as well if you right click. While that's opening up, I'll just pause recording. Okay, so now in space claim, we're going to sketch on the XY plane. So I just want to change the sketching plane. So if I just left click on the Y axis and then right click and go select new sketch plane, and you can just wobble your mouse around until you find it on the XY plane and just left click. So we're going to look in that direction. So just over here, views, front. So we're going to sketch the circle and then the outer bounding box, and then we'll set dimensions on it as we go. So circle, we're going to base that on the origin. So click the origin, drag out. So you can even type here if you wanted. So 1 meter is going to be the diameter of the cylinder. So it's going to take a second to scale out. Next, we're going to draw a rectangle. So I'll just draw it anywhere because I'm going to set the dimensions afterwards. So drawing that, press escape on the keyboard or just click off this. I'm going to use the dimension tool here. So click dimensions. I'm going to set the dimensions of this bottom line. So just click, and then hover over this number, click, and then drag 22 meters long. So this is a really large domain we're looking at. And then the length of this is, the height of the domain is 4.1 meters. So click on that 4.1, press enter. So then I'm just going to reset the view. So if I click here, I just click front again, or I could click the view, go to design and zoom. I could go zoom extents, do the same thing. Okay, so now I just need to set the distances. So if I go back to sketching pane and dimensions still selected, so I might just gonna get that out of the way. Click between the distance between the front and the center line here. That's going to be 2 meters. 2 meters. And then the distance between the bottom and the center of the cylinder is also going to be 2 meters. So hover over here, click 2 meters, press enter. We'll just reset the view again. So if you notice that the height of the channel is 4.1 meters, but the cylinder is actually located 2 meters from the bottom. So it's slightly offset to the bottom. So that's on purpose. So for low Reynolds numbers, it'll be essentially symmetric to flow, but for higher Reynolds numbers, you get vortex shedding. So by creating this slight asymmetry, it'll cause the vortices to shed in a predictable manner. Okay, so now we're actually different from the last video. We're just going to end the sketch here. So previously we filled it to create the surface, but if we click end sketch, that'll actually automatically take us out of the sketch mode, and it'll automatically create the surface for us. So it'll change the color of it. So just depending on which tab you're on, you might be on structure. I was on groups there, but if you change the structure, we have one surface here. So you can see it actually automatically noticed that there should be two parts of the surface. So we want to get rid of the part of the surface that's inside the circle. So we just click on that, left click on it, then you can right click and delete just down the bottom, just to get rid of that. So remember, we only want the surface where we're actually going to model flow. So we're just modeling the flow domain itself. So my computer's complaining about around here, but it'll struggle on. So we're pretty much ready, and we're just going to create the name surfaces, so not name selection. So unlike in the previous video, where we did that in the mesher, and now we're actually going to do it in space claim. So if you go to groups, so to define the inlet and the outlet, if we go to this groups tab, so then with select clicked on, you just left click on the inlet line and go up here to create NS, so that's create named selection. So that's a region where we can apply a specific boundary condition. If you just type there, so we're going to call it inlet. I'm going to do the same over in the outlet, so I'll click outlet, create name selection. And you might have to click again on it to type. Then I'm going to click top, and then if I hold control, click the bottom, that will select the top and bottom. So I'll create name selection. I'm going to call that walls. But a cylinder is also going to be a wall. So if we click on the cylinder and create name selection and call that cylinder. Just we want to keep that separate. We couldn't add that to the same walls patch. We want to keep it separate here because I want to calculate the drag on the cylinder, so I want to be able to select it independently. So that's us done. We have our inlet, outlet, walls, and cylinder. So we can click out of space claim now to go back to the workbench. Great. So next we can go into the mesher. So I'll just double click on the mesher. See we have a green tick here. It's fine. And we can wait for the mesher to open. Okay. It can take 30 seconds or so for that to load. So I pause the video, but when it first opens the mesh, you have to wait a little bit of time for it to actually load up the mesh. So just be patient. So if we click on the mesh, just below the mesh, we can see we have our inlet, outlet, walls, and cylinder defined. So we don't have to define them here. So click on mesh. And we're just going to use a default mesh size of 0.1 meters. So press enter, and we will just click generate. So of course, if you're doing a mesh sensitivity study, you may have to come back and revisit this step, like on multiple meshes. It's also possible to control a little bit more to maybe have a more structured mesh. But this is fine for now. So it's not that fine, but it's okay. Be careful though, don't, if you're setting this too small, you may find that you'll freeze your computer. So if I set that to 1e⁻5 and press go, it'll start to eat up a lot of the RAM on my computer, and it may freeze your computer and crash it. So just be careful, slowly scale it down if you're unsure. So we're done here. So we just close it out and go back, and then we're going to move on to Fluent. If you don't have a green tick here, which often is the case, you have to just go right click and then click update. And then when that's ready, we're going to open up Fluent. Okay, so next we're going to click on setup, and if you remember setup and solution, they're both done in the Fluent software. So you can see it's picked up that it's 2D, and here we're going to turn on double precision. Probably doesn't make too much of a difference, particularly for steady state. But these models are relatively quick, so we can just remove that potential source of error. So once again, just wait 30 seconds until it loads. So we'll just check all the settings are correct. So it is 2D planar, so it's not axisymmetric, it's just a 2D planar case, and we're going to go steady state. But when you go back to run a transient, you would set the transient here. We're going to keep steady state. And pressure-based density-based, you don't have to worry about this now, but depending on how, it's just a different way of solving the equations. So one might be more efficient than the other. We check the scale. It's from -2 to +20, from -2 to +2.1. That's fine. It's in meters. We click check to see everything's happy. There's no errors, and everything's fine. So now we can continue down through the left, checking all the settings. So we go to models, the model tree. Double click on that, and that'll open them here and also there. So first of all, we're going to run this case as laminar, and so we can just set that to laminar and ignore the turbulence models. Later on, if you want to learn on turbulence, we're going to look at RANS-based models, and then say DES, or detached eddy simulation, or LES. If it was a 3D model, we have an LES option here as well. So we're just going to go laminar. Nothing else. Materials, by default, it adds air. So if we double click on air, and we can also add extra materials. So we want to have water in this case. So we'll go to the Fluent database and scroll down and look for liquid water at the bottom. So water, liquid, H2O, click copy. You can see the properties about 1,000 kilograms per meter cubed, and the viscosity there as well. So kilograms per meter second, the same as it's equivalent to Pascal seconds. Close that, close this. So now we have water as an option in our materials. Go into the cell zones. This is basically where we set for their surface what type of material it is. Double click on that. It's set to air at the moment, but we can set it to water, liquid, because we added that option into our models list of materials. Click apply, close. Next one down, boundary conditions. We're going to set the inlet and outlet on the walls. So we look at the walls, and there will be the cylinder, and then what we call the walls, which is at the top and bottom. If we click on that, by default, you can see it correctly picked up that they should be just stationary walls, so walls that will slow down the flow. And our outlet will be correctly set to a pressure outlet, just based on the name, Fluent correctly predicts what you want. And for the inlet, we're going to, rather than have a constant velocity, we're actually going to specify a parabolic profile. So to do that, we're going to use what's called a user-defined function, or a UDF. So this is a way that Fluent allows us to customize our boundary conditions. So rather than them allowing all possibilities in terms of boundary conditions, they let you write your own little bits of code, in this case C code, to prescribe more complex boundary conditions. So Abacus actually does a similar thing called UMATs, or user material routines for material models. So if you click on user defined here and functions, click on that, and then interpreted. So interpreted means it's going to read C++ code and compile it. So if you click browse, and if you downloaded them from Brightspace, there's two files that are .c. So there's inlet velocity profile.c and vortex shedding inlet velocity profile. So they're almost the same if you open them. It's just one has a time ramp up of the velocity, and it's a higher velocity. So if we just use inlet velocity profile, and for this case, the steady state case one, click interpret. It's going to try to compile this. And so this is compiling a piece of C code into an executable, so a piece of code that I can run. We can click close. So now if we go to our inlet, we double click on that. Rather than specifying an actual velocity, we're going to say that the velocity and magnitude is set by a user-defined function. So that's our UDF inlet x velocity. So that's all we have to specify. We're saying it's normal to the boundary like before, but we're not going to type in the magnitude. We're going to say it's set by that function. Click apply, close. If you were to open that file, see what it looks like. It's relatively short, so you don't really need to know too much about C code, but Fluent allows certain functions to be overwritten. So define profile is a way to define a profile, and it takes in arguments of the x velocity, and then there's some other things as well, like position, and thread is to do with how it does the calculations. But basically here, this f profile here this is the actual formula. That's the formula just for a parabola in terms of y. So you y by y, so that's a y square. It's just a quadratic formula, and this is this value here is the average velocity. So it's 2e to the minus 5 meters per second. So if we change that number, that would change the average velocity. So this is actually setting the average velocity. And I'm going to close this over now. So that's our boundary conditions done. And if we did want to use the force coefficient calculators, so the drag coefficient and the lift coefficient, you'd have to set the numbers here. For example, based on the cylinder, Fluent is kind of smart enough that it will calculate the projected area of the cylinder and things like that. But you'd have to set the density to be whatever fluid we're using. So it's not smart enough to check what fluid you're using. You actually have to type it in here. So remember, this is just for post-processing if we did want to use the built-in force coefficient calculators, but we're not in this case. So if we keep going down, we can skip over these things: solution methods, controls, monitors. We're going to leave all the defaults, but report plots, this is one here. So we want to calculate the force on the cylinder. We could get a force coefficient, but we're not going to worry about that yet. We just want to know the total number of newtons that this cylinder experiences. So to do that, we'll go new, and we'll open up something like this. Over here, we'll go new force report and drag. So we're going to get the drag on the cylinder. So we can either set it to be a drag coefficient, so that's the actual force on our patch or cylinder and normalized with respect to the kinetic energy of the flow, but we just want to drag force in newtons. We just want to know what the force on the cylinder is in newtons. So we could pick the walls as well, but we're only interested in the cylinder here. So we go OK, and you can see the vector direction. So drag and lift, the difference is just our perspective on what direction we consider drag to be. So drag in this case is set to be x. And if we set a lift coefficient, it's or a lift report, it's exactly the same thing. It calculates the force, but just takes the component in the other direction, the y. So that's all fine. Click OK. It's going to plot this to a second window. It's going to plot it every iteration, and it's going to call it drag. So click OK. Close. We're all set up there. Next, we just initialize our flow. So it's a steady state simulation. The initial fields don't affect the final answer, but because it's a non-linear problem, they do affect a rate of convergence, how quickly it will converge, how many iterations it requires. So if we set a really good guess of the initial velocity and pressure field, then it may only need a few iterations. But if we set them all to a very terrible guess, it may take a lot of iterations, but they'll still go to the same answer. So we could just say standard, set everything 0, 0, 0. And we can set hybrid as well, typically is a bit smarter. So I might look at the inlet velocity profile and then propagate that through. So we'll do a hybrid iteration or initialization. So double click on run calculation. So we just have one, there's no time step as such because it's steady state. It's just does a bunch of iterations. So we'll just set it to 1000 iterations. So that's the maximum number of iterations it can do. So it'll either go to 1000 or it'll go to our tolerances, solution tolerances that we set. So we're hoping it'll hit the solution tolerances before 1000. So this is just the maximum number of iterations. So if we click calculate, and we're going to get two tabs opening up. If I get my little head out of the way. So we have this report plot 0. This is the one we created about the drag in newtons. And then we have a second one in scaled residuals. So you can see it's pretty quick. We don't have many cells. So you can see the two tabs. So the scaled residuals, like before in the previous tutorial, the solution will just keep iterating, in this case up to 20, whatever it is, 26, 27. I can scroll up in the terminal to see how many, 26. So it took 26 iterations to get the residual for the continuity equation, the x momentum equation and the y momentum equation, all to be under 1e to minus 3. But equally, we can plot the drag force versus iteration. So it starts relatively high. It's a small number, so the default plot just thinks everything's 0, but it starts relatively high and then it iterates down to its steady state value. So in problems like this, rather than looking at the residuals to decide if something's convergent or not, you could look at a physical quantity like drag. And once the drag stops changing with iterations, then you could say it's converged. So if we saw it stopped here and it's still clearly going down, then maybe we should set the solution tolerance to be tighter than 1e to minus 3 because we know the physical quantity of drag is not converged. Okay, let's look at some of the fields. So we could just jump straight to CFD-Post, but we'll just have a quick look here in Fluent as well. So if I double click on contours like before, we'll look at velocity first, and the magnitude is fine. Click display. So a couple of things to note. The inlet velocity profile here, you can see it's highest in the center, lowest on the outside. So that is our parabolic inlet profile. If you're writing your own UDF, you should really just double check or verify that what you think you coded in is what you intended to code in. So you might plot the line along here and just check those values are the same as what you created in Excel, for example. So you can see the average should be 280 minus 5, and the peak here should be 4. So it's almost exactly 4. If the mesh was finer, we would get one cell with 4. So that's the parabola. The average is like half the peak. So you can see what happens is it accelerates as it goes below and above the cylinder, and it's almost symmetric. The cylinder is a little bit closer to the bottom, so it's a little bit faster on top. And then downstream from the cylinder, the effect of the cylinder disappears, and you get a parabolic profile as well. Again, which pretty much is the same as the inlet. So the inlet and the outlet are almost the same here. We can have a quick look at pressure as well and display that. So when the fluid slams into the cylinder, you get a peak in pressure. So the fluid has to be slowed down by the cylinder, so you get a buildup of pressures. And then as you go past it, you get a drop off. So you get drops off here as well on the sides where the flow is detaching from the cylinder. So it's, the streamlines are separating away. So you have high on the inlet, low on the outlet, because pressure drop drives fluid flow. So the fluid flows from high pressure to low pressure. That's fine. We can look at even things like path lines here in Fluent. We can do the CFD-Post as well. So you look at path lines and released from surface. So if we tell it where the inlet is and press display, it will show us some streamlines. So the streamlines go around the cylinder. Just near the back of the cylinder, they actually detach. So we can't see it here, but there's actually 2 smallish counter-rotating vortices that form just behind the cylinder. And so the shape of those and shape of flow are dictated by the Reynolds number. So in this case, the velocity profile that was selected was to cause this laminar flow with vortices behind it. So when you look at higher velocities, then you get vortex shedding and other interesting phenomena. So we just close out of this and accept the defaults. And then we're going to finish by opening CFD-Post and just to plot some values along lines. So back here, just double click on results. That'll open up CFD-Post. So CFD-Post is open now. Sometimes it'll open in the background. It'll just be down here. So you just need to left click on it to make sure it opens. Okay, so I might just click on Z over here just to look that on. So we can look at contours like we did. So we can go insert a contour, look at the velocity again. So we can go okay, look at the velocity and apply. And there's different settings that you can change. All domains. Look at the surface, location. Sorry, you have to pick one of the front or back planes. So they're called symmetry here. So just go all domains and symmetry, so you can see the flow around the cylinder here, like we saw before, and you can play around with the contours if you want to as well. So what we're going to do here is we're just going to plot along a line like we did in the first tutorial, but we're going to do streamlines as well. So we're going to create a line like before. So insert line and call it line 1. I'm going to just put it a little bit downstream from the cylinder. So the diameter of our cylinder was 1. So I'm just going to put it 1 in front of it. So we go 1, minus 2 will be the bottom of the domain, and then 2.1 will be the top of the domain. We can set maybe multiple samples as well if you wanted to plot the profile there. So we can make a chart like before, but also what's useful is we can look at streamlines. So you can click on the little buttons on the top here, but you can also go insert streamlines. Streamlines 1. So we can say where they start from. So we could start them from the inlet, like we did in Fluent. We can click apply. And that will show the streamlines. We just have to turn off the contour to be able to see them. So we can see our streamlines there. 25 is a good number of them. Maybe change it to 50. So we can see, like we saw in Fluent. But we could also start them from our line 1. So line 1 goes here. So if we click apply on that, from the line it releases them. As you can see, they only flow in the direction of the flow. But the benefit here is because we sampled through the vortices, the training vortices, we actually can see their structure. If we set the direction here to forwards and backwards, it'll integrate in the direction of flow and then backwards as well. So then we can generate the full picture itself. Very good. So that's the end of this tutorial.